your rep. I'm sure he has. So I'm good. So hello, are we together?
Yes, Prof.
Yes, we can hear you, sir.
That's all right. So we are going to continue. I had mentioned this before, but I needed to start here.
Prof, we can hear you. Unmute your mic, Prof, sir. Prof, unmute your mic, sir. Prof, unmute your mic, sir.
Right, I have been granted access now, so I've unmuted. Can you hear me now?
Yeah, yes, Prof.
Right. Okay. So we are going to continue with concentration, like I mentioned. Right. So I said the single most important parameter in environmental fate transport studies is what we call chemical concentration. If you cast your mind back when we're talking about dose, you cannot just say that maybe 20. You cannot just say 20 of a particular chemical was administered or was measured or was introduced. It has to have a unit of concentration. So we can say 20 milligrams of a particular chemical was administered. That milligram is a concentration of 5 milligrams per liter. That milligrams per liter is the unit of concentration. So in that case, you can say that you are using the concentration factor, to describe how much of the material or the chemical that you are administering, so to speak. So, like I said, chemical concentration is the most important parameter when it comes to the study of fate of these chemicals and transport of these chemicals. And it is defined as a measure of the amount of that chemical in a specific volume or mass of air, mass of water, mass of soil, or mass of sediment, or mass of any organic or any material at all that you are, dealing with. So not only that, concentration is a key quantity in freight and transport equations. Chemicals concentration in an environmental medium also in part determines the magnitude of its biological effect. So if you say 20 milligrams per liter and you said 5 milligrams per liter, already you can you have been able to describe the magnitude of of that particular chemical. And the higher the concentration, it is expected that the biological effect will be more than when you have a smaller concentration. So most laboratory analysis methods measure concentration. The concentration is just quantity of that chemical, that you are trying to look at or measure, right? And they all have units. So the choice of units for concentration depends in part on the medium and in part on the process that is being measured or described. Like I said, if you are determining a particular chemical in soil, you know that, let's say you are determining a particular agrochemical, or you are determining a particular heavy metal in soil. You know that the soil is a solid, component or matter. The metal that you are determining in soil is also solid. So the unit of concentration will have to be gram per gram, all right? That is mass over mass, something like that. So it could be milligram per kilogram or microgram per gram, because the analyte or the chemical is a solid, and the medium in which you are determining the chemical is also in solid. So if you are determining, for instance, a heavy metal like copper in water, you know that the medium in which you are determining that copper in is liquid. But you know that the copper is a metal, all right? So it will be gram per liter or gram per mil, so to speak, because water is measured in volume, right? So in that case, you may have something like milligram per liter or microgram per mil, right? Because the medium is water or the medium is liquid. So that is how the units are played, around. So the choice of units, like I said, for concentration depends in part on the medium and in part on the process that is being measured or described. So in water, the common expression of concentration is mass of the chemical per unit volume of water, right? And many naturally occurring chemicals in water are present at levels of few milligrams per liter. That is mg strike, milligram per liter, right? So the fundamental dimensions associated with such a measurement are MLT, supposed to be MLT, or milligram per cubic liter. So the letters M, L, and T are referred to as mass, length, and time. So all these, form part of the unit of concentration and so on and so forth. Now, another common unit of concentration in water is known as molarity. Molarity. Molarity is a mole of a chemical substance, or a mole of a chemical substance is composed of 6.02 times 10 to the 23 atoms or molecules. For those of you who did secondary school chemistry, I'm sure you must have heard about Avogadro's constant. So this is what you mean by Avogadro constant. It says that for 1 mole of a substance, there are 6.02 times 10 to the 23 particles, all right, or molecules of that substance. So molarity refers to the number of moles per liter of solution. So if you have the number of moles per liter of a solution, we refer to that as molarity. Molarity. So there is a related unit too that describes concentration. That one is known as normality. Normality. And normality refers to the number of equivalents of a chemical per liter of water. What do we mean by equivalent? Equivalent is the amount of a chemical that either possesses or is capable of transferring in a given reaction. 1 mole of electronic charge. Okay, I'll give you an example in the note. There's an example in the note. Just follow me. If a chemical has 2 electronic charge units per molecule, all right? If you have a chemical that has 2 electronic charge units per molecule, 1 mole of the chemical constitutes 2 equivalents. What do you mean by that? Take example of sulfate, SO42 minus. How many charges do you have there? You have 2 negative charges. So in this case, it is equal to 2 equivalents. And a 1 molar solution of sodium sulfate is 2 normal. Is 2 normal, right? Because the sulfate is coming from, in this case, from sodium sulfate. Normal, question or concern at this point based on what I've explained? Hello? Hello? Hello, guys? Hello? Hello, are you with me?
Yes, sir. We are with you, sir.
We are with you, sir. We are with you.
Thank you.
You're on mute.
Good morning, Prof.
Good morning. Right. So in soil, I have given you a background on concentration, but I want to take you through the notes so that you appreciate better when you are reading. So in soil, expressing concentration as mass per unit volume for soil carries the possibility of ambiguity, because soil undergo volume changes if they are compressed or are expanded. So accordingly, it is often more useful to express soil concentration as mass per unit mass. I think that is what I said before. I'm just repeating myself for clarity. Such as milligram per kilogram, because the mass of soil does not vary with changes in the degree of compaction of the soil. Okay? So for air, which is highly compressible, expression of chemical concentration as mass per volume is even more ambiguous. The volume of a given mass of air changes significantly with changes in pressure, right, and temperature, and thus the chemical concentration, when expressed as mass per volume, also changes. Now, consider the following situation. If initially there is 1 microgram of benzene vapor, that is a gaseous substance, per cubic meter of air, and the barometric pressure decreases by 5%, the concentration of benzene as expressed in units of mass per volume also decreases by 5%. Because the air expands while the mass of benzene remains what? Constant. So expressing the benzene concentration as mass of benzene per mass of air removes all ambiguity, because changes in the temperature and pressure do not affect the mass of air present. So for air, we usually represent the unit per cubic meter instead of just volume, right? So ambiguity can also arise when a laboratory reports the concentration of a chemical that can exist in more than one form, that is species, without reference to particular species. For example, if the concentration of nitrogen in a water sample is reported simply as 5 milligrams per liter, it is unclear whether 1 liter contains 5 milligrams of nitrogen atoms or 5 milligrams of one of the nitrogen species present, such as nitrate, nitrite, ammonia, or ammonium ion. So in such a situation, clarification for the laboratory performing the measurements must be obtained to understand the actual chemical mass present. Furthermore, if the species associated with a concentration is not known, a conversion from mass to moles is not possible. Okay, it's not possible completely. All right, so these are stories, but numerous other options exist for specifying a concentration. Common ones are parts per thousand, that's PPT, or parts per million, or parts per billion. Okay, for the soil and air cases, just mention ppm on a mass basis, numeric equal to milligram of chemical. So this is just trying to let you know how these chemicals are measured in the various medium. If it is air, how do you represent the unit? If it is soil, how do you represent the unit? If it is liquid, how do you represent the concentration unit? So that is the basic thing that we're talking about here. Hello? Hello? Are you with me? Hello?
Yeah,
We're with you, sir.
we are with you.
All right. So the medium in which you are determining the how do you call it? You are determining the
Concentration.
the chemical, okay, would have an implication on the unit, so to speak. Yes. Somebody asks whether dose and concentration are the same or there's a difference. And I think someone has clearly given an answer there. Dogara Gingin has given the correct answer. So yes, they are related, but there are slight differences. as you can see in the message box. Somebody, I saw a hand up. All right. So let us look at mass balance units and what we refer to as control volume. Now, this is where you need to be attentive, because this part involves a number of calculations, and like I said, if you are not able to grab anything in now that we are doing these lectures, then you must make it a point of duty to be on ground when we are doing revision, because I will concentrate much more on areas that involve calculation, since we cannot, interact very well in this area where calculations are involved. And I wouldn't want to go and start calculating things on paper and sending it to you. So you need to be attentive. You need to concentrate at this point and get every detail that I'm giving you now. And that will also help you when you are doing the revision during that time, and even when you are going through the notes. So 3 possible outcomes exist for a chemical that is present at a particular location in the environment per given time. And the chemical can remain in that location. It is possible that a chemical that is being deposited at a particular location may remain there for some time, depending on some of the environmental conditions that we have looked at, including half-life and so on. So the chemical can remain in that location. That is one possibility. I told you there are 3 possibilities. The chemical may remain in that location. 2, it can be carried elsewhere. All right? It can be carried elsewhere. We have talked about transport by a transport process. It could be through runoff. It could be through wind action. It could be through erosion, and so on and so forth. But it can be carried away from where it was initially found, or it can be eliminated. Elimination here includes being transformed into another chemical, so it does not occur in the state in which it were before. That is what we refer to as elimination, or eliminated, or transformation. It can be transformed into another chemical. And this very simple observation is known as mass balance or mass conservation. Remember the law of conservation of energy that says energy is neither lost or what? Created, but can only be transformed into another kind of form of energy. So energy is not lost. Now, it is also believed in mass balance that if you are able to introduce, let's say, a particular amount of chemical in an environment, it does not matter whether that chemical was transported. It does not matter whether that chemical was eliminated. The most important thing is that at the end of the day, you should be able to account for all the parts, all
I'm not hearing the proof again. I don't know whether it's only me that is facing the challenge.
The line has been so inconsistent, going off and on. My
Please, Mr. Samuel Alaku, can you turn off your video, please?
Hello? Hello?
Yes, Prof.
Hello?
Welcome back.
So there's an interruption through a call. No, I'm using my phone internet, so there was an interruption through a call. Sorry about that. Right. So I was saying that like the law of conservation of energy, which says energy is neither created nor destroyed. It can only be transformed. So it is believed that the chemicals that we deal with, when they are introduced into a medium, it does not matter what the medium is, be it water, be it soil, it is expected that you should be able to account for the various processes or stages in which the chemical may have, passed through, okay? And be able to put those individual parts together to give you what was initially introduced, so to speak. So mass balance is a concept. It's a concept, although it is not entirely perfect, or it's not entirely 100% accurate because of some contending issues or factors that affect it. We'll look at that shortly. So mass balance is a concept around which an analysis of the fate and transport of any environmental chemical can be organized. Mass balance also serves as a check, all right? Serves as a check on the completeness of knowledge of a chemical's behavior. That is where I say if you are able to account for the individual portions of the chemical and you put them together, it also helps you to check whether what was introduced has been recovered or not. So if at a later time in an analysis, the original mass, are you hearing me, of a chemical cannot be fully accounted for, then there is an incomplete understanding of how transformation and transport processes are affecting that chemical. So it is a kind of an account. It's a kind of a check, okay, to see that, yes, we are aware of where this chemical is moving to or transforming to, and so on and so forth. So the accurate modeling of fate and transport results from an understanding of every process contributing to the mass balance of a chemical. So you must be able to understand the processes that are contributing to the mass balance of the chemical, and so on and so forth. Else, it will be difficult for you to account for it. So, implicit in the application of the mass balance concept is the need to choose what is called control volume. That is why you have control volume there. Control volume. Control volume. Control volume. So what is a control volume? What is a control volume? Assume that you have a container, like maybe a tank that has water in it, and you are introducing maybe some chemicals into it, so to speak. All right? That could be also considered as a volume. But let's look at what we have here. A control volume is any closed volume across whose boundaries we propose to account for all transport of a chemical. Control volume is any closed volume across whose boundaries we propose to account for all transport of a chemical, and with whose boundaries we propose to account for all the chemical initially stored, as well as all processes, that is sources or sinks, that produce or consume the chemical. So the mass balance expression for any chemical in any control volume during any time interval can be written as follows. Any question, any concern at this point? Is there any question, any concern at this point? Hello? Are you following?
Yes, sir, we are hearing you.
That's okay. Not just hearing, you're understanding what I'm saying. That's the most important thing. If you don't understand now, like one of my lecturers will always say, if you don't understand now, you go and understand when you go to the hostel. Because when you get to the hostel, you'll be forced to read and understand.
Yes, sir, we will read it up. For now, I cannot lie. We are just following what you are doing. Your understanding is far from us for now.
That's okay, but
Thank you, sir.
You get through. It's just a matter of time.
Amen.
Yeah. So we mentioned a number of things here. We're talking about control volume. We say control volume is that volume, okay, or space, closed environment that we want to account for the transport of the chemicals. And we want to also account for all the chemicals that are initially present, okay, as well as those that have been consumed, and so on and so forth. So, like I said, you have a chemical in a particular environment, it's either it will remain there. First, you have a certain amount in place. So the next thing that will happen is what? it may be transported. Okay, may be transported. It may be eliminated. So mass balance is just to account for all of these chemicals in those routes, right? So we have a general expression for mass balance, and is given as change of storage in mass. Mind you, if the concentration, if you have a concentration of a substance, for instance, in a tank, let's say 20 milligrams of that material in that tank of water. That tank contains water, and you have that chemical in that water. And maybe after some time, you check for the concentration, and you discover that there was no change, reasonable change in the concentration, or the concentration remains constant. In that case, you discover that change of storage in mass will be equal to 0, because the concentration has remained constant over a period of time in that particular tank of water, something like that. So change of storage in mass is equal to, and these are some of the things that will bring about change of storage in mass, is equal to mass of the chemical or substance that is transported in, okay, transported in, minus mass of substance that is transported out, all right, plus the mass that is produced by all sources, then minus the mass that is eliminated or transformed. Hello? Did you get that formula well?
Yes, Prof.
Right. So change of storage in mass is given as mass transported in minus mass transported out. Because as you have in, you have out. And then you have mass produced by sources. These sources might be within the system, and then minus the mass that is being eliminated. That is the equation for mass balance. If I were you, I will write this thing on a paper. I will write on a paper, because we are going to have a number of these equations from now. This is equation 2. I think we have up to 6 or 7 or 8 before we conclude the course. So if that is okay by you, let's move forward. Now, the mass balance expression in a control volume can also be written in terms of rates. That is, instead of mass, you can talk about rate of transport, rate of production, rate of elimination. When you have rate, it has to do with something with time. So the mass balance expression in the control volume can also be written in terms of rates. That is mass per time. That is how much of the mass is being removed per time, how much of the mass is being transported per time, how much of the mass is being eliminated per time. That is rate. All right? That is why this one is slightly different from equation 2. So control volumes are chosen to be convenient and useful, while the choice of a good control volume is somewhat of an art and depends on both the chemicals and the environmental locations that are of interest. The control volume boundaries are almost always chosen to simplify the problem of determining chemical transport into and out of the control volume. I'm going to give you an example. Take this example now. I am going through the notes this way so that you can understand or follow. And if you have a question, you can ask. Now, as an example of an environmental pollution problem requiring the choice of a control volume, now consider a lake. Consider a lake. Consider a lake. You know that you have a lake, and a lake is capable of receiving a number of chemicals, is capable of eliminating them, is capable of storing, is capable of transforming them. So a lake is a good example of a control volume. That is what we are talking about now. So if control volume was, you were not understanding what a control volume means, you can take a lake, for instance, as a control volume, right? So as an example of an environmental pollution problem requiring the choice of a control volume, consider a lake that is receiving industrial effluent from a discharge pipe, okay? To establish a useful volume within which we could describe the fate and transport of chemicals in the effluent, we might choose the entire lake. So we can now assume that the entire lake is our control volume, all right? And it is receiving discharge from an industrial world, from an industry, so to speak, through a pipe. It is being, discharged into that lake. So that is like it's coming in, something like that. Now, let us define the boundaries now. Let us define the boundaries. Now, the upper boundary of the control volume is the lake surface. We can now take the lake surface as the upper boundary, all right? Transport across this boundary is described by the general principles that govern chemical transport between water and air. Mind you, at that surface, you have water and air interacting at the surface. So that gives you the upper boundary, all right? Transport across this boundary is described by the general principles that govern chemical transport between water and air. That gives you the upper boundary. Now, listen. For some chemicals that are non-volatile, these are chemicals that do not vaporize completely, all right? For some of these chemicals that do not vaporize, that is chemicals that do not really move from a dissolved phase. In this case, chemicals that are in water are said to be in dissolved phase. Maybe not all of them, but there are some that are in water and are dissolved. So non-volatile chemicals may not be able to escape from the water to the atmosphere or to air. All right? So we say that for some non-volatile chemicals, that is chemicals that do not rapidly move from a dissolved phase in the water to a gaseous phase in the air. That explanation is there. This transport rate is negligible because it is hardly that you get them, removed or transported from the water to air. We can consider that that process is non-existent or is negligible. We can ignore, transport through that medium or through that action. So for many other chemicals, enough knowledge exists to make reasonable estimates of the air-water exchange rate. For others, based on factors such as the volatility of the chemical, the rate of chemical diffusion, You know what I mean by diffusion? That is movement of a chemical from region of high concentration to a region of low concentration. If you put a perfume on your body, after some time, you will discover that that perfume has diffused. It is moving from where it is sprayed to an area or areas where it is not sprayed. But that does not mean that all of it will diffuse or we leave. You still have some, some of them on your body, so to speak. Now, that is what happens, or that is what is happening or happens at the upper level of that volume. In this case, the lake. Okay. Somebody is saying that it's thrown into confusion. But just calm down. You will get. So you will. Okay. Thank you. It says the explanation is beginning to bring more sense. That's okay. That's fine. So, mind you, we have established the upper boundary of the control volume here with respect to the lake. We said the surface of the water, okay, between that the water and the air surface. That is what we are referring as the upper boundary. Now, let us establish the lower boundary, okay? Now, the lower boundary of the control volume might be chosen to be just above, listen, just above the uppermost layers of the lake's bottom sediment. Okay? The lower boundary of the control volume might be chosen to be just above the uppermost layers of the what? Lake's bottom sediments. Because you know that if you go into the lake or you go into the river, for instance, what you have beneath are what? Sediments. Sediments. So that is where we can establish our lower boundary. Now, listen very well. Water that is seeping into or out of the lake sediments. Mind you, water that is seeping into or out of the lake sediments is then one transport mechanism. It's one aspect mechanism by which a dissolved chemical could cross the lower boundary of the control volume. Do you understand? Do you understand that statement? Let me repeat it. Water that is seeping into or out of the lake sediments is then one transport mechanism by which a dissolved chemical could cross the lower boundary of the control volume. All right? Now, the lake control volume might also receive chemical input from an inflowing stream. There might be an inflowing stream. Okay? In the first place is water that is seeping in and out of the lake sediments. Okay? In and out of the lake sediments is one mechanism by which dissolved chemicals could cross the lower boundary of the control. Take note of that very well. Now, the lake control volume might also receive chemical input from an inflowing stream. Now, the rate at which a chemical enters the lake from the stream could be estimated. Mind you, the rate at which a chemical enters the lake from the stream could be estimated by multiplying the stream flow by the concentration of the chemical in the stream. So if you multiply the stream flow, okay, to be estimated, the rate at which a chemical enters the lake from the stream could be estimated by multiplying the stream flow by the concentration of the chemical in the stream. Now, to complete a mass balance on a chemical within the control volume, internal consumption, okay, internal consumption, there is internal consumption, production, and storage. All of these I've mentioned earlier even in the formula. Let me look at messages. Right. Lower concentration until they are eventually distributed. Yes, correct. Same flow, concentration of chemical in the stream. Yes, that's true. Yeah. Right. So to complete it must be quantified of the thing. You must account for production and storage of the chemical. Also must be taken into, must be quantified. So in some cases, source and sink strength can be estimated based on knowledge of chemical and biological composition and physical attributes of the lake. So if the lake is well mixed, get this point very well. If the lake is well mixed, storage of the chemical in the lake control volume at a given time can be estimated as a product of the chemical concentration in the lake water and the total volume of water in the lake. You will understand better when we take example. Now, note that if you look at these two equations, I want to talk about these two equations. Look at, go back. Can you see? You have change of storage in mass. In this third equation, you have rate of change in storage of mass. So we are talking about these two, equation 2 and equation 3. The difference between equation 2 and 3 is that in equation 2, you are talking about change of storage in mass, just the mass, okay? But in equation 3, you are talking about the rate, okay? That is mass per time, The mass, how much of it is stored per time, how much of the chemical is transported in per time, how much of the chemical is transported out per time in the lake, for instance, how much of it is produced per time by the various sources, and how much of it is eliminated per time. That is the difference between the first and the second. So what we are trying to say is that in this second, look at the left hand of the equation. You have change of storage in mass. Now, look at here, the left, rate of change in storage of mass. So, look at the 1, 2, 3. Look at the third paragraph here. It says, note that the left-hand sides of equations 2 and 3, which I have shown you, are 0. Listen very well, are 0. I think I made this statement too before now. They are 0 if storage does not change with time. If storage does not change with time, then then if storage does not change with time, then this will be equal to 0. The rate of change in storage of mass will be 0. If there is no change in time, there's no change in storage, it will be what? 0. The same thing applies here. If there's no change of storage in the mass, here it will be 0. If there's no change, it means it will be constant. Okay? So that's the explanation there. So note that the left-hand side of equations 2 and 3 are 0 if storage does not change with time. This is one example of, you may not understand this, but there is something we call in chemistry steady state approximation. That is the state where we assume that every other constant, every other variable in a given equation equal to 0. That is why you are talking about 0. That is what steady state approximation says. Like in this case now, let me just use this one and explain what that means. I don't want to go into that so that will confuse you. At that point, there is no change. But if there is change, then there will be a value there. But because there is no change, that is why you are having a value 0. But if there is change in the storage, definitely you are going to have a value. For instance, if you have initial value to be 10 milligram, for instance, and after some time, you now have, let's say, 7 milligram. In that case, there is change, is it not so? That will be 10 minus 7. So what is the change there? 3. But if you have 10 milligram of the chemical in the volume or in the control volume in the lake, for instance, and then after some time, you measured and you still have 10 milligram. Mind you, change has to do with something minusing another one. That change you are having there is to minus one quantity to, one property from, and one subtract one from another. So if you now have 10 milligram per liter as initial concentration, and after some time, you measure and still have 10 milligram per 10 milligram, 10 minus 10 will give you what? 0. That is the meaning. But where there is change, it will be 10, then 8, then that will be 10 minus 8. Okay, initial minus the final. Because the initial will always be what? Bigger than the final. If there is a change, after some change, such a time, you will not get the same concentration, then it will change. So at that point, that left-hand side will not be 0. But where there is no change at all, you expect that the rate of change in storage of mass will be equal to 0. So when you sum this, at that point, if you sum this together, it will give you 0. That is what the equation is saying, nothing more than that. So let me take it again. Note that the left-hand side of equations 2 and 3 are 0 if storage does not change with time. This is one example of steady state. You don't need to bother yourself about steady state because I've explained. I've explained that. Everything on earth is chemistry. So this is one example of steady state, a description that applies to any problem in which quantities do not change with time. You hear that? Quantities do not change with time. So if there's no change with time, then it is 0. Mathematically, all derivatives are said with respect to time are 0 in a steady state systems. So steady state assumptions often simplify the analysis of a problem, but should not be invoked when transient, that is time varying. Where there is a variation, when there is variation, the steady state approximation will not apply because it will not be 0. If all terms but one are known, If all terms but one are known in the mass balance expression of equation 2 and 3, the control volume can be used to estimate an otherwise unmeasurable transport source or sink term as shown in example 1. Before we go to example 1, I want you to look at what this thing is saying. Now, if you are able to know, for instance, what that statement is saying is this: if you are able to know the rate of change in storage of mass, okay, you are able to know transport rate in, or mass transport rate out, or mass production rate by sources, and you don't know mass of elimination rate by sinks, you'll be able to find it. Is it not so? It's just for you to make this one subject of the formula and then calculate for it. So if you are able to know to know some of all the variables except one, you can calculate for that one because you know the values for others. That is what that statement is saying, nothing more than that. That's what that statement means, nothing more than that. Now let's take example, one example. Now you just have to be attentive here because there are certain there are going to be some assumptions and so on and so forth. Now, just take a look at this question. And then after here, you can also look at it yourself very well. You have an issue, when we return by 1 o'clock, we'll deal with some of your concerns and so on and so forth before the revision day. Now, the question says, a discharge pipe from an industrial fermentation process releases into a lake. I just let me not read it. I want one of you to read this thing for us. I don't want to read it myself. I want one of you, any of you should read it to our hearing. Thank you very much. Vera? Vera's hand was up and then off. Okay. Vera, you're going to read for us. Okay, Vera.
Thank you very much. Yes, sir.
Read it for us and read it gently.
Okay, sir.
Go ahead.
A discharge pipe from an industrial fermentation process releases into a lake small amounts of various alcohols, and it is desired to estimate the rate at which alcohols are degraded in the lake. One of them, butanol, in brackets C4H9OH, is released to the lake at the rate of 20 kg per day. Butanol is measured in the lake water on several occasions at a concentration of 10 kilograms per m³. No butanol is detected in the following stream.
In the
average stream flow at
in the inflowing stream.
Okay, in the inflowing stream.
Yes.
Average stream flow at the outlet of the lake is measured to be 3 times
10 raised to power 4. 10 raised to
power 4 meter cube per day. What is the magnitude of internal sinks of butanol? What are the limitations of this mass balance analysis?
Right.
Should I continue?
No, just hold on now. I wanted someone else to read so that even myself, I can listen to it. And did you Okay, Dugeri is putting up his hand. Let's, no, let's, yes, Farida,
Good morning, sir.
please, can you speak?
Can you hear me?
Go ahead.
Okay. A discharge pipe from an industrial fermentation process releases into a lake small amounts of various alcohols, and it is desired to estimate the rate at which alcohols are degraded in the lake. One of them, butanol, C4 908, is released to the lake at the rate of 20 kg per day. Butanol is measured in the lake water on several occasions at a concentration of 10 raised to power minus 4 kilograms per meter cube. No butanol is detected in the inflowing stream. Average stream flow at the outlet of the lake is measured to be 3 times 10 raised to power 4 meter cube per day. What is the magnitude of the internal stream of butanol? What are the limitations of this mass balance analysis?
Thank you very much for reading. Praise, you too, you want to read? Hello, Praise.
Yes, hello, sir. Good morning, sir.
You want to read or you want to ask a question?
I was still thinking you demanded for somebody to read it out.
Two people have read already. You didn't hear them?
So maybe I should have lowered my hand. Sorry, sir.
Okay, but go ahead. Maybe continuous reading will give us a better understanding of the question. Go ahead, please.
Right. The question says, a discharge pipe industrial fermentation process release into a lake small amounts of various alcohol, and it's required to estimate the rate at which alcohols are degraded in the lake. Butanol is released to the lake at the rate of 20 kilograms per day. The butanol is measured in the lake water on several occasions at a concentration of minus 10 kilograms per meter cube, but the butanol is detected in the following streams. Average flow at the outlets of the lake, which is measured at 3 times 10 raised to power 4 millimeter per day. What is the magnitude of the internal things of the butanol? What is the limitation of this mass balance analysis?
Thank you. Now, why did we go for equation 3? That's the first thing I'd like to ask you. Why did we go for equation 3 instead of equation 2? Hello? Is anyone there?
Hello, good morning.
Go ahead. Is that Shinshima?
It's Wangi, sir.
Okay, Wange, can you speak? Although your
yes,
hand, I didn't see your hand up. It was Shinshima. So hold on for Shinshima, please, so that we don't look. So Shinshima, can you speak? Shinshima?
Yes, I can hear you. Thank you, sir. I
Speak,
think,
please.
okay, I think the reason is for the question. It stated that the ethanol has been degraded. So that is the reason why we're using the equation 3, sir.
Okay. All right. Any other person? Understanding starts from the question. Who's the next person?
Someone answering in the chat box.
No, but that I want somebody to speak. In as much as they're answering there, I would also want them to speak, because sometimes when you say something, it carries more weight than writing. So
hello, sir.
I've seen the charts.
Hello, sir. Good morning,
Yeah. Good morning.
Yes, sir.
Who is on the line?
Looking at the last, yes, sir. Good morning, sir. Looking at the last line of the question, sir.
Yes.
The question says, what are the limits of the mass balance analysis? That is, since it said we are looking for the limit of the mass balance, so we have to look for the mass elimination rate by the sink. So that's why we are using equation 3, sir.
Okay.
Yes, sir.
All right. But I want someone to say it again. Another person. I want to give a number of opportunities.
Indeed. Me now, because of my lecture, as soon as.
So who? Okay, Shishma, you still want to talk? I think you are spoken. Shishma, you want to talk again? Hello? Hello, Shishma? Oh, Shishma. Right. Someone has already answered that question. Okay. And let's look at what Oban has to say. Okay. Oban. Hello, Oban, comfort.
Good morning, sir. Thank you so much for the lectures.
Good morning.
Sir, we are using equation 3 because the rate at which the discharge was released is stated in the equation. That's the reason why we are using equation 3.
Mm-hmm. Right. Okay. If you look at equation 2, if you look at equation 2, equation 2 is talking about change of storage in mass. Equation 3 is talking about rate of change in storage of mass. Go to the question. The question says a discharge of blah, 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 blah. One of them, butanol, is released to the lake at the rate of.
Yes.
At the rate of. It's because of the rate. It's because of the rate that we're using equation 3. Because equation 3 is talking about rate. Talking about rate. It's talking about rate. So it is not because we are asked to, look at the elimination, so to speak, but it is because it's rate. It is rate. Someone has already answered that in the chat box, and it's because of the rate. It's not because of any other thing, because that is the equation that concerns the rate factor. Okay.
Rate at which, yes.
Mm-hmm. So it's because of the rate. Now let's go into it now. Now, I may not go into the structure of the equation, how it has been rearranged, but mind you, if you look at equation 3, just cast your mind back, look at equation 3. Where is mass elimination rate by sinks? The elimination is the last one, is it not so? The first one you have is rate of change in storage of mass. So it means you have to make mass elimination rate or elimination by sinks the subject of the matter. Did you hear me?
Yes.
Good. So, and that is what the question is asking us to look for. What is the magnitude of internal sinks of butanol? Sinks are the ones that eliminate these chemicals. Are you hearing me? Sinks are the ones that eliminate these chemicals. So elimination rate by sinks is what we are looking for. So you have to make it subject to the formula. So if you make mass elimination rate by sinks subject to the formula, you are going to have mass transport rate in minus mass transport rate out, okay, plus mass production rate by sources. I want to make a point here. Look at the mass production rate by sources. We are told that it is possible that you will have an inflow, is it not so? You have an inflow stream, okay? But mind you here, look at, it says no butanol is detected in the inflowing stream. It means it's one of the sources of production. Are you hearing me? But in this question, they said no butanol is detected in the inflowing stream. All right? So it means that one we have a value of 0, so to speak. But again, look at the same mass production of rate by sources. So you can have more than one source. That is what I want you to know. You can have more than one sources. You can have 2, you can have 3, you can have 4, depending on, you know, how they are being produced in the lake. Then minus rate of change in storage of mass. Even that one, you will discover that rate of change of storage in mass is constant, because they said butanol is measured in the lake water on several occasions. Did you hear that? This is where thinking comes in. Thinking comes in. I'm doing this so that by the time I get to the solution, you will not have issues. So it says that butanol is measured in the lake water on several occasions. So it was measured on several occasions, but the concentration remained what? 10 raised to the power minus what? 4. So which means it is 10 raised to the power minus 4 minus 10 raised to the power minus 4. Is it not so? It will give you what? 0. Did you get that point? Hello? Did you get that point?
Mass elimination.
We go to the chat box quickly. We have 1 or 2 responses there. No butanol is detected in the inflow stream, yes, because we desire to know the rate at which the alcohol is being removed. Is being removed. Now let's okay. Dugeri wants to say something. Let's hear from him. Hello, Dugeri.
Prof, good morning, sir.
Good morning. Can you speak?
Good morning, class. I want to appreciate you for the lecture so far.
Thank you.
The fact is that as we're having our revision week, which will be physical in school,
yes,
I suggest we treat those questions those issues that are critical here during our physical lectures.
Yes.
My suggestion, sir, because this is giving us some of us that are not mathematics oriented. I think it's confusing us here. Thank you, Prof.
It's all right. It's all right. At least, but it's good that you follow it here. Maybe you will just sleep and wake up and discover that you have understood the whole thing.
Thank God.
Don't be defeated. Don't be defeated.
All right.
They are just simple concepts that need some critical thinking, nothing more than that. And everything is there. That is why I wanted people to read by yourselves, and maybe the understanding will also be improved. You will not be lost out. Okay.
Yes, sir, Prof. Thank you, sir.
There is somebody that wants to speak. Who's there? Agba, Ben, Stephen, can you speak?
Can I go ahead, sir?
You
Yes,
go
sir. Good
ahead.
morning, sir.
Go ahead.
Good morning,
Yes.
class.
Morning.
Thank you so much, sir, for the wonderful.
Yeah, go ahead. Be snappy, please.
Yes. Can you hear me, sir?
Yes,
All
go
right.
ahead.
All
Go
right.
ahead.
Okay. I was saying thank you so much for your patience with us.
Thank you. Go
This
ahead.
is a general question I've always wanted to ask. And it's a general question, not specifically on our class. Now, there's always this assumption. I see people, for instance, somebody wants to take a bottle of Coke. The person will dissolve it or maybe add a cup of water and still consume the whole bottle of Coke. My question now is, has the person reduced the concentration of that, the content of that bottle of Coke? And if the person has consumed the whole bottle of Coke, will it have the same effect on the person as the other person who did not dissolve that bottle of Coke inside maybe certain quantity of water? It's a general question, like I said, but it's something that has actually, I've had a conversation with a doctor friend of mine, for instance, when she told me that her opinion was that the person who is taking the concentrated bottle of Coke like that, the effect on the person will be different from the effect on the person who probably poured it into a cup of water and consumed. So, what's your take on this, sir? Thank you so much.
Yeah, the only thing is that the concentration, mind you, the volume, concentration is a volume thing. So as you increase the volume, you discover that the concentration will reduce. Okay? So adding water to it, what you are doing is that you have only increased the volume of it. Therefore, you're going to have less concentration. But that doesn't mean that it is different amount that you are taking. It is the same amount that someone who has taken together, that has taken without adding Coke has taken. It's the same amount. The only thing is that the volume has changed and the concentration has also changed. Yes, the person who has taken it without diluting is going to observe higher, how do I put it? If it is negative effect or adverse effect, we will observe much more than that person who diluted. Okay? I don't know whether I've made some sense.
Okay. Okay, sir. Okay, sir. So, in essence, what you are saying is, if, like you said, if there is an adverse effect, the person who did not concentrate, who did not dissolve, would get the effect, the impact or the effect more and faster than the other one that did not
faster.
than the other one
Yes,
that did
fast.
not.
Exactly.
Okay.
Faster.
Okay.
Yes. Yes.
Okay, but at the end, is there a possibility that they may still experience similar effects at a long run?
Yes. Yes. It is. Yes.
Okay,
because
all right.
You are taking the
All right.
same,
Thank you so much, sir.
the same amount. Right. Let Wange speak quickly, and then we continue. Yes, Wange.
Good morning, sir.
Good morning.
Thank you for the wonderful lecture. I will start first of all by contribution, and I will want to react to the practical question that one of our very own has asked about Cook. In addition to what you have said, Prof.
Okay.
You know, Coke contains carbonates, and in other words, it's a gas that is dissolved in a solvent and cooked under pressure. So if you open the Coke, the first thing you hear is the gas that has been, pressurized in the drink you are taking. So if you drink directly from the Coke, you are taking also a concentrated form of the CO2 gas that has been compressed there under pressure. So at that level, you experience a different sharp taste. And if you have gastritis, you also experience bloating. Your stomach will be filled up faster. But when you also put the Coke in a cup, what you have easily done there is that you have increased the surface area of the liquid you are taking, the Coke you are taking. So the gas must have escaped. That gas, that carbonate that has been dissolved in that drink under pressure must have escaped because of the difference between the pressure and the atmospheric pressure. It will escape. So you are taking something that is less concentrated now. I
He
don't know
said
whether
that
you understand.
he said that someone who takes Coke directly and someone who dilutes it with water, who mixes it with water before taking, are they going to have the same kind of experience the same kind of adverse effect, or one will experience faster than the other?
No, they will have the same adverse effect. You have all explained that. I'm only adding to what you have said in a different way.
Oh, okay, it's all right.
So
All right.
I'm talking about the carbonate that is there. So even without adding water, but once you put it in a cup that has a more opening, you will experience a different kind of concentration. So when it comes to the CO2 concentration, it has a different level concentration that you will be taking it. Thank you. Then the other one, sir, please, these formulas are very long.
Yes.
So I was thinking that for easy understanding, we'll look for symbols and give to the rate of change in storage of mass and that of mass transport rate, mass transport rate in, mass transport rate out, and mass elimination rate by sink, and also mass production rate by source. But we give them symbols and define them from the beginning. So if we understand those symbols, then it's very easy to reduce the equation to something that we can easily manipulate, so that from the equation we can deduce the parameters. We can say that mass transport rate out, P.
It's all right. I've gotten what you're saying. This is masters.
Thank you. The last one is a question. You spoke about volume control. So should we look in the environment, in environmental monitoring or analysis, should we look at volume control as also a baseline?
Baseline?
Baseline, like you are taking a control volume. That control volume you are taking is a reference point after your analysis. I don't know if you can relate that.
What I'm referring to as control volume is, take example, you take a lake, for instance, okay? Take a lake, or you take a particular river, or a particular stream, something like that. It's not that
okay, sir.
You are looking at
then the other question is about dimensions. Sometimes we have a single question, we have parameters mix. Instead of having only kilogram, you have kilogram. One will carry kilogram per day. The other one will carry grams per day. Another one will carry micrograms per day. So if you are faced up with that kind of scenarios in parameters dimension, is it ideal to convert all of them to kilogram or to convert them to grams? I don't know if it is SI unit you use or you just adapt to the situation. Thank you.
Like I said, it depends on the medium. It depends on the medium in which you are looking at the chemical in. We have SI units, we have standard units. So those that have standard units, you convert them to the standard unit. But those that do not have, you can leave them that way or convert. For instance, now, if I were you, if I were given a particular assignment and I have different units, maybe CMQ, you have some CMQ, some in liters. Are you hearing me now? Liters. I would prefer that you convert from liters to CMQ, something like that. So it is left for you to decide that you go with one form of unit. If it is per day, you know, you can also convert per day to even per hours or 24 hours, something like that. So it depends on what you do. But I think generally, I would say that if you feel strongly, you can convert. You can convert to have a uniform unit instead of maybe centimeter cube and then mix with liter like that. You can convert liter to cm cube to liters to have uniformity. Now it depends on what you want. Okay.
Thank you, sir.
So let me answer you about what you are saying equation. This is a master's class, and it is expected that after here, you can also sit down and see how you can shorten this note and absorb everything or almost everything that is here in a way that you feel it is best. So you can decide to abbreviate the formulas or the equations as you want. But if we were doing this thing practically in the class, that would have been one of the things that I would have done to agree that maybe a elimination rate will give it this symbol, this one will give it this symbol. But since I may not be able to do that right away, you can also do that at your own level or private time. And that will also help you to understand better. Okay? So that's
Yes,
okay. That's fine. So let me just try and round up here so that you. So we now, if you look at this equation now, say mass of elimination is equal to rate by 6
It's as if network must have thrown Prof out again. So let's wait until he's able to come back.
Okay, Prof is back.
Sorry, yeah, there was an interruption.
Yeah, we can hear you, sir.
Right. So I said you have a mass of elimination. That is what we are looking for in this relationship. So by assuming, mind you, by assuming that no butanol exchange with the atmosphere, this equation can be written more explicitly for the mass balance. We can rewrite it in this form. We can rewrite it in this form. Now, internal sink rate is equal to discharge by input rate. Okay, input rate. That's that input rate coming from that pipe plus stream input rate, okay, minus stream output rate, plus as internal sink rate is equal to discharge pipe input rate plus stream input rate minus stream output rate plus internal source rate minus rate of change in storage. Now, let us look at the answer. You may appreciate better here. Now, by considering the equation term by term, the discharge pipe input rate of butanol is given to be what? 20 kilograms per day. Note that the stream input rate is 0 because they say you should assume that, you know, by assuming that the lake is well mixed, that is, the butanol concentration is the same everywhere in the what? In the lake. The stream output rate is given as what? 3 times 10 to the power 4 times 10 minus 4. Now let's go back. Let's go back. Now look at. No, it's not. It's a place. Look at the first paragraph here. Look at the first paragraph here. Just look at it. The lake control volume might also receive chemical input from an inflowing stream. The rate at which a chemical enters the lake from the stream could be estimated by multiplying the stream flow by the concentration of the chemical. Did you get that? Then go back here. No butanol is detected in the inflowing stream. So average stream flow at the outlet of the lake is measured by multiplying this value. Look at it in the question. the flow at the rate, the inflowing stream, the average stream flow at the outlet of the lake is measured to be 3 times 10 to the power 4. Okay, so that you have to multiply this by the concentration, which is 10 to the minus what? 4, for you to be able to get what? The stream output rate. Check it very well. You appreciate what I'm talking about, which is equal to what? 3. Now, assume there are no internal sources of butanol. So the internal source rate is what? 0. The internal source rate is what? 0. So given that the butanol concentration in the lake water seems to be a steady state at 10 to the minus 4, because they say there is no change, then the rate of change in storage is what? 0. Is 0. Therefore, the mass balance is internal sink rate now is equal to what? It's equal to 20. It's equal to 20. What is 20? 20 is the discharge pipe input rate of butanol is 20 kilograms per day plus the next one is what? Mass transport in is 20 minus mass transport rate out is 0. Is 0 minus 3 kilograms per day. Right. Since it's on the system, so I'm finding it difficult to go back and explain, come back. But please look at the numbers and then try to substitute them, and then see whether it makes any meaning out of it. If it doesn't, like I said, we will always return to the class and do the revision, and there we'll be doing the numbers, we'll be working with the numbers properly. But here I'm finding it difficult to go back, come back, and then see how I can get them out clearly. But go through it. Anywhere you have a challenge during our revision, which is face to face, we will, go over this thing properly again and see that everybody follows it. So, what are the limitations? These are the limitations. These are the limitations. They are there. You will look at them, read them, and then follow. Then we have another aspect that we need to look at, the physical transport of chemicals. Has to do with the physical transport of chemicals. Just telling us the different ways in which these chemicals can be transported, different ways in which they can be transported. Okay, I told that most physical transport of chemicals in the environment occurs in the fluids, and it's air and water, primarily through bulk movement. Okay, that is from one location to another, and that is referred to as advection, right? And it's due to bulk large-scale movement of air or water as seen in blowing wind. So as wind is blowing, there's a possibility that, okay, it will carry these chemicals along, and flowing streams, that is convection. As a similar term often implies vertical advection of air or water resulting from density differences. So as these chemicals are moved from one point to the other, they create density differences, because what you have at the initial point will not be what you have at the end of the day. So it creates differences in their densities, so to speak. So you have another way in which these chemicals are transported. They are transported in a random way, okay? And that has to do with mixing processes within the fluids. Here, there is no definite direction of movement or flow. It can be a random form. Here, a chemical moves from one location in the air or water where its concentration is relatively high to another location where its concentration is lower, creating what is called concentration gradient, so to speak, and due to random motion of the chemical molecules. So that is referred to as molecular diffusion. The molecules are diffusing from a point where they are high in concentration to a point where they are the concentration is low. Random motion of the air or water that carries the chemical. They could be turbulent. Okay, if the air is carrying that chemical in a random way, we could refer to that as turbulent diffusion. Okay, or a combination of the two. All right, transport by such random motions are also called diffusive transport. And this diffusive transport is often modeled by what is called Fickian. You have Fick's law. There is somebody that has given a law. It says the rate of diffusion is directly proportional to the concentration of the material. That if you have plenty of the material in the system, then it will diffuse much more than the one that does not that has low concentration. So concentration is a factor of diffusion. That is what Fick law says. So sometimes the motions of the fluid are not entirely random. Sometimes they are not entirely random, and they have what is called a discernible pattern. A discernible pattern, but it is too complex to characterize. In this situation, the mass transport process is called dispersion. It's called dispersion. That is where it is so complex. The movement is so random, very complex to understand. We refer to that as dispersion. And it is also commonly treated as a Fickian process, even though in some situations it may only approximate through Fickian transport. So what is Fickian transport? Fickian transport is movement that is not in one direction, movement that is in different direction, or a chemical is moving maybe by the action of air, and after some time you discover that if the air changes direction, the transport of that material will also change. Okay, that is what we are referring to as Fickian transport. Okay, hello, 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 are you with me? Hello, hello, hello.
Hello, sir. We can hear you, sir.
Okay, so I'm trying to explain what Fickian process is. I said it is a movement of these chemicals in an unpatterned way, in a way that is not definite or straight. Okay, so random kind of transport of the chemicals. We refer to that as Fickian transport. So we are told that the bulk motion of fluid is common throughout the environment. The bulk motion of fluid is common throughout the environment. And this advective motion is described mathematically by the direction and the magnitude of its velocity. So if a chemical is introduced into a flowing air or water, the chemical is transported at the same velocity as the fluid, because it will be the speed of the medium that the chemical will also acquire. So widespreading due to Fickian transport, may occur at the same time, as described in the next section. Now, the center of mass of the chemical moves by advection at average fluid velocity. Maybe we'll stop there. When we return in the afternoon, we will look at it again because of time. So, any concern at the moment? Any question? If not, when we resume, we'll go over what I've mentioned before we continue, for clarity's sake. Hello? Hello?
Yes, sir, we can hear you.
All right. So we'll see much later. Okay. We have this this last part is calculation, but God will help us. I'm sure. By the time we meet face to face, you will appreciate it better. Right. So see you later. Okay.